Right, my dear children. Now, let's see how to identify these changes in our environment. So, there are like two types of changes which can occur in our environment. So, to demonstrate the two types of changes, I have a paper, an A4 sheet, you can see it. So, I will take half of this A4 sheet. I'll take half of it. The same A4 sheet, I'm going to take half of it. And this is my one half and this is the other half. Now what I'm going to do is, first of all, I'm going to take this paper, the first half, and I'm going to tear it into smaller pieces like this. Right? Into several smaller pieces like this. See, this is the first one, the first half. I have teared these. I have teared the first piece of the A4 sheet into smaller pieces like this. Right? Then this is the second half of the A4 sheet. The second half. For this half, I'm going to do a certain different thing. I have a spirit lamp with me. So I'm going to light it up. Right? I'm going to light it up. And now what I'm going to do is, I'm going to take this half and I'm going to burn it down. Right. Right, my dear children. The first half, the second half. So when you observe these two instances, it's clear to us that when you take the first half, these ones, these papers are smaller in size. There is no change in composition of the paper. Whatever the material which the paper has made up with, those materials haven't changed. But you can clearly observe the size of the paper has got changed. That's it. Size has been changed. But still, it's a paper. We can write whatever the things we want in these pieces. Even though these are smaller, we can write any of these things. Right? The second half. This half is being destroyed completely due to fire. Means that this is not paper now. The paper has changed into a different kind of a substance. The composition of these substances are not same as these papers right now in the first instance. Right? You can clearly observe even the color has got changed dramatically. Right? Now, if you've been asked to write down certain things on these ashes, can you write it? Of course, you can't. Right? And if I'm going to touch these things, you can see here, a small, very small powder has been created. So it's very clear to us that after burning this paper, different substances has been created, and these substances are not same as the previous substances. So I'm going to ask you a simple question once again. Can you take these ashes and convert those ashes into the same paper like this? Even like a small bit of paper like this, so that we can write something? Your answer would be no. By collecting these ashes, we can't convert or we can't create a piece of a paper. It's because that the composition or the materials which contained in these ashes are not same as the paper. All the materials contained inside the paper has got changed now. So it's clear to us that the thing which is happened when I'm going to burn this paper is irreversible, and it is referred as a chemical change. In here, when I'm going to tear the paper down, even though I'm going to make smaller pieces of papers, their composition or how these are being made haven't changed at all. The composition of the paper, composition means the amount and the type of matter contained inside this paper. So it haven't changed, even though the size has been changed, right? So once again, if I'm going to collect these papers into a correct order, up to a certain level, I can recreate that A4, half of that A4 sheet. Up to a certain level, not to 100%, but to up to a certain level, I can recreate the A4 sheet. It's because that the thing which is happened in here is a physical change. Just the physical nature or how the particles are being, how the substance or way of the substance, the nature of the substance has got changed. That's it. The composition or the nature of the particles haven't got changed in this occasion, right? So therefore, it's clear to us that this is a physical change. From larger material to smaller materials are being created here, but in here, by destroying all the materials or all the paper contained earlier, new substances, ash, being created. So these are the two main types of changes that we can observe in the environment. In the first one, just only the physical change. In the second one, the chemical changes. So we'll observe somewhat different things rather than these burning things. Burning of paper rather than the burning the paper, we'll observe some different things or different activities, different experiments to observe what sort of a thing is a chemical change and what sort of a thing is a physical change. So let's carry out some different activities to identify those examples as well. Right, my dear children, now we are about to investigate another experiment. So in this experiment, I'm going to use some salt and dissolve it in water, and by heating, I'm going to evaporate all the water in it. Okay. So by that way, I'm going to observe whether this change which occurring inside the salt solution is a chemical change or else a physical change. Right. So I have salt with me. In this petri dish, you can observe the salt. So salt, it has a white color structure, white color nature, somewhat white color, and it is in crystalline nature. Crystalline means it's like powder. See, small powdered crystal. So now I'm going to take small amount of salt and put into the beaker like this, and now I am going to add 50 milliliters of water to the beaker. So let's add water. And I'm going to take the glass rod and stir it very well to dissolve all salt in it. So when I'm dissolving salt, gradually the salt crystals will dissolve in water, and the crystalline nature or the salt will totally disappear. Right? It will totally disappear. So you can clearly see that in here, right? So I'll mix somewhat. Right. So my dear children, you can clearly observe that there is no salt in it. All the salt have been now dissolved inside the water container or the water beaker which I have right now. Some of you may think, now salt has been disappeared. No, means that this is a chemical change. But what happens if I'm going to heat this container and vaporize all the water in it? Can we observe the salt once again? So let's conduct the activity and we'll see whether we can get the salt which we dissolved inside the beaker after vaporizing the water. So now what I'm going to do is I'm going to use this tripod and place it on the Bunsen burner like this. This is the Bunsen burner, and the steel mesh to hold the beaker. Now I'm going to light up the Bunsen burner and I'm going to heat it down. Right. So now I am heating the beaker very well. So let's observe what will happen in the end when I am heating it. So we'll take somewhat time because we need to evaporate all the water in the beaker in order to observe or in order to get our necessary observations. So be patient and observe what will happen to the beaker when vaporizing the water. Right, my dear children, now see the beaker is gradually heating up. And if you observe clearly, you can see there are some small bit of like powder is like dust or a powder is getting deposited at the bottom. Right? If you could observe, you can see like there is a powder which is going to the bottom of the beaker. Very small drops or very small powder like thing is depositing at the bottom. Right? Observe very clearly. You can see even in this area, you can observe that white color powder. So let's give it somewhat more time so that the water will evaporate completely, and we'll observe what will happen at the end of the experiment. Right? So we'll give it somewhat more time to evaporate water. Right, my dear children, now we are at the final stage. Now almost all the water has been evaporated. Now we can clearly observe those white powder around the beaker. Right? See, if you check the wall of the beaker, you can clearly observe that white color powder. So that white color powder is the salt that we dissolved in the earlier stage, right? So in here, even though we have dissolved salt in water, when heating, we can get the amount of salt which was dissolved earlier in the same stage as powder, right? Now if you measure the amount of mass, you can get the same amount of salt which was dissolved in the earlier stage. Now it's because that when dissolving salt in water, the nature of the substance or the composition of the substance, composition of the salt is not getting changed. Salt is chemically referred as sodium chloride. Means that it contains sodium and chlorine. So sodium chloride or salt, the composition of salt or composition of sodium chloride is not getting changed when this thing is going to dissolve inside water. So when vaporized in water, we can observe at the bottom the precipitation of salt. So here once again the salt has been precipitated. So we can observe at the end the salt crystals. Right, my dear children, now I have vaporized all the water in the beaker. So at the bottom, see, you can observe the salt, right? So I'm going to use this crucible. I'm going to show it to you how the salt has been deposited inside the beaker. See, all the salt that we dissolved in the initial stage once again can be observed at the bottom of the beaker. It's because that this dissolving process, dissolving salt or sodium chloride, is just a physical change. The salt crystals or salt powder, I have dissolved it in water. Even though I am going to dissolve it, right? See, even though I am going to dissolve it, their physical nature is going to change, and that's it. So their chemical structure or the composition of the material is not going to change at all. So therefore, that's why we can get all the salt once again back to the beaker when I'm going to vaporize the water. So it's clear to us that dissolving salt in water is just a physical change. Here the salt crystals is going to dissolve inside the water to make a salt solution. So when I'm vaporizing water, I can revert the process once again to obtain salt powder, right? So dissolving salt in water is a physical change. So we'll observe what are the other examples. What are the other examples that we can observe in our day-to-day life to get some idea about physical and chemical changes. Right. So let's proceed to the next things. Right, my dear children. Now, this is the next activity to observe or to get some idea about physical and chemical changes. So I have a metallic ribbon. See? This is magnesium. This ribbon is called as magnesium. So it doesn't have, even though it is a metal, you can see that it doesn't have any kind of a luster. Luster means there is no shiny surface, right? You can see it. It's because that magnesium is covered by an oxide layer. Magnesium is going to bond with oxygen in our nature or in our atmosphere, and an oxide layer can be observed around magnesium. So when you are using magnesium for an experiment, you have to, like, by using a small bit of a sandpaper, you have to like scratch it. So when you scratch it, very well like this, right? You can get the metallic luster of magnesium once again, but magnesium is highly reactive. See, you can observe the shiny surface. But the thing is that magnesium is highly reactive. Reactive means it's going to bond with oxygen quite fast. So when I'm going to keep this thing of the magnesium stripe in our normal environment for 1 or 2, 3 days, the shine of the luster of the magnesium will once again reduced, and this ash color oxide layer can be observed. So I have some magnesium stripes which I already scratched by using the sandpaper. Now what I'm going to do is, by using this crucible and my spirit lamp, I'm going to burn this piece of magnesium to observe what has happened, or what kind of a thing is going to happen after burning a piece of magnesium stripe. So let's see whether this thing is a physical change or else a chemical change. So let's burn the piece of magnesium to observe whether this is a physical or else a chemical change. Right, my dear children, observe. So I'll use this petri dish to put the waste. I'll use another one. I'll use another piece and I'll burn it. See the color? Let's try another one and let's see what are our residues. Right, my dear children, now you have observed what is going to happen when you burn a piece of magnesium like this. So let's see whether that hard nature of magnesium, now when you take this magnesium piece, now this is a magnesium piece which I have prepared. It's not like a powder, you can observe it clearly, it's not like a powder, it's hard, right? See this thing. Now this is the residue or the remainder after the burning process of magnesium. See, it's getting into a powder. It's getting into a powder. See, it's a white color powder right now, right? It's a white color brittle powder. Brittle means breaking down quite easily. So here you can observe that, see, you can observe the white color very well. So this white color powder is referred as magnesium oxide, because during the burning process, magnesium is joining with oxygen, or it's burning with oxygen. You know that in your previous grades you observed, or you know that during a burning process, or when something is burning, oxygen is very important, right? So when you burn something, when you burn anything, that material is going to bond or react with oxygen gas, and the nature or the chemical structure, the composition of the material is getting dramatically changed. It's changing into a different form. So in the earlier part, we burned a paper, and I told you that that's a chemical change. Now here also you can see a white color powder. So burning a piece of magnesium is a good example for a chemical change, right? So these chemical changes are also referred as chemical reactions. Here the magnesium has reacted with oxygen gas to produce this white color magnesium oxide powder. So burning a piece of magnesium is a good example for a chemical change or else a chemical reaction. You can't invert or you can't change this powder into once again piece of a magnesium stripe. It's because that these chemical reactions or these chemical changes cannot be reverted back to original position or to original stage. So we'll carry out some other experiments in order to get some idea about these physical and chemical changes. Right, my dear children. Now, in this activity, we'll be observing somewhat other different examples to get some idea about chemical and physical changes. So, especially here I'm going to show you some physical changes, right? So, we'll observe what kind of a physical change is going to occur when I'm going to heat these pieces of wax. This is solid wax pieces, right? You can observe very clearly solid pieces of wax. See, right? Now what I'm going to do is I'm going to take a boiling tube and I'm going to insert these wax pieces into the boiling tube gradually, and I'm going to heat it by using the spirit lamp over there. So when I'm going to heat this solid wax, you know that it will turn into a liquid. The solid wax will turn into a liquid. So it's clear to us that when I'm going to heat this container or heat this boiling tube, the solid wax will turn into a liquid, means that solid nature is getting changed into liquid nature or liquid state. So we'll carry out the experiment to get the relevant observation. So I have a crucible here to hold the boiling tube, right? Then the spirit lamp, so I'm going to heat it. I'm going to heat the boiling tube gradually. So you can see clearly the solid wax is turning into a liquid inside the boiling tube. See children, you can see that it's clearly turning into a liquid. Right. So here you can observe the liquid form of the wax, right? Now what I'm going to do is I'm going to keep this system and allow it to cool. I'm going to keep this system and allow it to cool. So what will happen when cool in this system? Let's observe what will happen when cool in the this liquid wax. Okay. So after that I'm going to explain like what kind of a change occurred here. Actually, you know that this is a physical change, but I'm going to specially explain the name or the term which is given for the each of the change in instance or the state. So I'll keep this boiling tube in a position so that it will cool gradually. Right, my dear children. So, observe what can you see at the bottom of the beaker. You can observe the solid wax once again. See? So, I have cooled the liquid very well. See, I have cooled the liquid very well. And I have turned that liquid wax once again to a solid wax. So, this is a wonderful example for a physical change. So, when I am heating this solid wax, it is getting turned into a liquid wax. Once again, when I am cooling this liquid wax, it will turn into a solid wax. So, this is a wonderful example for a physical change. Here, the solid has changed to a liquid. The solid state has changed to a liquid. Once again, the liquid state has changed to the solid by reverting the temperature or the heat energy which is supplied. So, this is a good example for a physical change. Now, let's move on to observe another experiment to see these state changes in matter. Right, my dear children, now in this activity we will be observing some other cases where we can identify its state changes in matter. So I have some ice cubes with me right now. Right? So this is ice cubes. So you know that ice cubes are made up with water. When I'm going to freeze water by cooling, you know that ice cubes are going to be created. So I'm going to have some ice cubes. I'm going to put into this beaker, the smaller beaker. Right. Now what I'm going to do is I'm going to supply heat by using the spirit lamp and heat this thing up. So when supplying heat gradually to the system or to the beaker, this will turn into, this means ice will turn into a liquid. Right? Ice will turn into a liquid. Now in the earlier case, you observed that the solid wax also turned into a liquid wax. Now in this case, solid ice cubes is turning into liquid ice, liquid water. So we'll give some time. It's heating up gradually, so we'll give it somewhat more time. So you can here observe that gradually the ice is going to melt down and turn it into a liquid. So like in the previous case also, we heated up a piece of wax, some pieces of wax, and during that process we could observe that the wax is going to convert, or wax is being converted into a liquid. So once again when I'm going to cool it when I'm going to cool it down, the liquid wax turned into a solid. So like half of the ice cubes now being turned into liquid water. So we'll give some more time so that all the ice cubes or all the ice will turn into liquid. Right, my dear children, now you can see that all the ice cubes, all three ice cubes has been converted into liquid water right now. So I'm going to supply further heat. I'm not going to stop. I'm going to supply further heat, right? So let's keep the system in the same position so that it would heat up quite more. So my dear children, now when you take a solid, here you observe two states or two examples where a solid is getting converted into a liquid. So in the first case, we heat up several pieces of wax and we turn those things into liquid wax. Okay, we turn those things into liquid wax. Here we heat up some ice cubes and we turn those ice cubes into liquid water. So here the solid state is getting changed into the liquid state. This transition of state from solid to liquid, the transition of this state from solid to liquid is called as a fusion. This is called as a fusion, right? So this transition is specially called as fusion, or in normal terms we refer that thing as a melting. So here we have melted solid wax and turned it into a liquid wax, right? And ice also we have melted to make into a liquid water. Now the system has somewhat heated up. Now I'm going to place, I have a petri dish with me, right? See, I have a petri dish with me. Now I'm going to place this petri dish somewhat above the system or the beaker. Here you can observe when I'm keeping this thing at the top of the beaker, some kind of a vapor is getting formed on the petri dish. See, you can observe it clearly. Some kind of a vapor, some droplets are getting created on the petri dish. So this vapor is getting deposited on the petri dish. So this vapor, you know, these are water vapor, and when it is going to hit on the petri dish, it's getting cooled down. See, you can observe it very well. See, there are droplets of water in here, right? So I'll keep it once again. So you can see that water vapor is getting deposited on the petri dish. Right. So when I'm placing this petri dish above the, system like this, right? You know that the vapor coming from the system is going to hit on the petri dish, and after some time the water vapor is going to be cooled down and turning into water droplets. So in this state, you can see that the gaseous water vapor is going to deposit as liquid droplets on the petri dish. So in this state change, we can observe a gas is getting converted into a liquid on the petri dish. This state change is specially referred as the condensation. So here we can say that water vapor has condensed into water droplets when I am placing this petri dish above the beaker, right? So these are some examples that we can observe the state changes in matter. So let's continue some other examples rather than these things to observe what are the other instances where we can observe these state changes. Right, my dear children, now we are about to discuss another state change, right? So in this activity, I have small bit of, so my dear children, these are iodine. These small balls are iodine crystals, right? So now I'm about to heat these iodine crystals and to observe whether these crystals are getting turned into a liquid or not. Now in the earlier cases, in earlier activities, when I was heating solid wax and when I was heating ice, first of all, ice turned into liquid water and then into a vapor. When I'm heating wax, solid wax turned into a liquid wax, right? So let's see what will happen when I'm going to heat these iodine crystals. So I'm using a crucible, and by using the crucible I'm going to add few iodine into the crucible like this. Then I'm going to heat it down. Right, so I have added some iodine into the crucible. So I have added few pieces of iodine crystals here, right? So I'm going to keep it and heat the system to see what will happen in the instance change or the state change. So we'll heat up and see this iodine will turn into a liquid or not. So let's heat it, and while it is heating, I'm going to place this funnel on it. Right, you can see that the iodine is going to heat up gradually. So my dear children, you can see that here it's clear. Now iodine has not been turned into a liquid. You can see that a purple color gas is going to emit. See, a purple color gas is going to emit from the system. So I'll use this tissue paper. You can see a light purple color gas which is getting emitted from the system. A light purple color gas, see? Right. So my dear children, in here, in this instance change or in this state change, we can see that the iodine is directly getting converted into a gas like this, a small bit of a purple gas. It's getting directly converted into a gas. We can't observe the liquid nature of iodine. There is no liquid nature in iodine. Means that when I'm going to heat these iodine crystals, it's directly getting converted from solid to a gas. The intermediate liquid state cannot be observed, right? And on the walls, you can observe the solid nature of the iodine as well. If I'm going to cool it down somewhat further, we can observe the solid nature of the iodine as well, right? So here, the iodine has been converted into a gas straight from solid. We can't observe an intermediate state which is a liquid, right? So now I'm going to remove this funnel and I'm going to show you, right, that there is no iodine left in the crucible. See, there is no iodine in the crucible. All the things has been converted into a gas. So this form of converting, this state of converting directly a solid into a gas is referred as sublimation. So this state change is referred as sublimation. When a solid is getting converted directly into a gas without the intermediate liquid state, this state change is referred as the sublimation. Right, my dear children? So all of these experiments which we conducted are related with the state changes, right? So we'll move on to the classroom to study further things related with the lesson. Right, my dear children? Now, in these set of activities, we'll be observing like what kind of things or what are the evidences that we can provide during a chemical change, right? So when a chemical change is going to occur, what sort of a thing will happen into the system and what kind of thing is going to emit from a system, right? By using those things, how we can say whether a chemical change has happened or not. So in the first step or in the first activity, we'll be heating lead nitrate. So here PbNO3, and again within brackets you can observe there is 2. So this is the chemical formula, PbNO3 twice, lead nitrate. So we are going to heat up lead nitrate in this activity to observe what kind of thing or what will happen during a chemical change. How we can say whether a chemical change has happened or not. What are the evidences to show that there is a chemical change or not. So I'm going to use some amount of lead nitrate first, and I'm going to insert this lead nitrate into, so lead nitrate, going to, I'll show the nature of lead nitrate. See, so this is a white color powder, lead nitrate. This is the nature of the lead nitrate. See, it's like salt, lead nitrate, right? So now I'm going to add this lead nitrate into my boiling tube and I'm going to heat it down to see what are the observations. So I'll put this thing into the spoon. Right, so I have used small bit of lead nitrate because when I'm going to heat this thing, somewhat toxic gas is going to emit, right? So I'm heating just a small bit of a lead nitrate. So now I'm going to hold this by using the holder and let's heat the system. Right, my dear children, now let's heat the system and let's observe what kind of a thing is going to emit when I'm going to heat this lead nitrate in the boiling tube. Right, now my dear children, I'm going to heat the system. Observe the changes very well. So let's get the observations. See, in this situation, some small bit of explosions can also be observed within the boiling tube. So we have to be careful when doing this experiment. Observe the changes very well. See, a gas is going to emit. like a brownish color gas is going to emit. Right, you can observe now there is a brownish color gas, and now when we see the residue is somewhat like brownish color also, you can observe, right, like in the earlier case. Now once again I'll keep it in here. Now I'll use some lead nitrate by using this. So here check the color of these two. See, it's been changed to a like yellow color substance, and you could clearly observe that a brownish color gas was emitted, right? Means that new substances have been created. During the burning of lead nitrate, a new substance was created. A gas was emitted, a brownish color gas was emitted, and the container is also like reddish color or reddish yellow color, right? So in this situation we can observe the formation of a gas, right? A formation of a gas could be observed, clearly observed. We could observe clearly there was a gas which is emitting when I'm going to heat the lead nitrate. So the first evidence in a chemical change is that if a gas is going to emit during mixing of two substances or when burning or any other cases, in that situation a chemical change has happened. So that's why new substances or new gases are getting produced. So in this activity, it's obvious to us that lead nitrate has converted into, or it has undergone a chemical change and to produce a gas. Right, now let's continue with another activity, another experiment to observe what are the other evidences so that we can say in a given system a chemical change has occurred. Right, so we'll continue with the other experiments and we'll see what are the other evidences. Right, my dear children, now let's conduct this activity. Let's conduct this activity where we are going to use copper sulfate, right? And we're going to make a solution of copper sulfate, and I'm going to add a piece of iron nail in here, right, to see whether there is a chemical change or not. And if there is a chemical change, what kind of an evidence is being provided with the experiment if there is a chemical change, right? So I'm going to conduct the activity and we'll see like what kind of a change is going to occur. What are the new substances which is getting created within the system. So by using the new substances, we can say that a chemical reaction or a chemical change has occurred. So first of all, I'm going to add some amount of copper sulfate. So this is copper sulfate. So copper sulfate is a blue color crystal powder, and also you can observe, or if you want, you can get copper sulfur as a crystalline solid like a piece of rock, a blue color, right? So this is copper sulfate. To dissolve these copper sulfate quite easily, I have taken in the powdered form. So now I'm going to add this copper sulfate into the boiling tube. Right, I'm going to add Then using a wash bottle, let's add some water. And now let's mix it well. So let us add some more water. Right, so I have prepared my copper sulfate solution here. It has a light blue color. You can see it very clearly. It has a light blue color. Right. So what I'm going to do is, now I'm going to place it over here. And we will measure the temperature of the system or in the copper sulfate solution here. So we need this temperature, the measurement of temperature, in order to check whether there is a heat change or whether there is a temperature change in the system during a chemical change or not. So to observe it quite well, I'm going to use this thermometer and I'm going to measure the initial temperature of the copper sulfate solution. So I have the thermometer with me. So let's insert the thermometer and we'll get a reading. Right. So here the initial temperature of the copper sulfate solution is about 30 degrees of Celsius. Right. It's 30 degrees of Celsius. The initial temperature, you can see it clearly in here right now. See. The initial temperature is 30 degrees of Celsius. Right, now I'm going to insert the iron nail into this container. I have a cleaned iron nail, right? So I'm going to insert this cleaned iron nail into the system like this, right? Now we'll leave it some time and observe what kind of a change is going to occur in this system. Right, my dear children. Now you can observe there is a difference in the color. See, there is a difference in the color. The color has somewhat lightened up. Right? In the earlier case, initially it had some kind of a blue color. Now the blue color has reduced. Now I'm going to insert the thermometer and we'll observe how much is the temperature in it now. Right, now you can clearly observe the temperature has rose up to 5 degrees. Up to 5 degrees means now the temperature is at 35 degrees of Celsius. Earlier it was 30 degrees of Celsius. Now after the reaction, now the temperature is at 35 degrees of Celsius. 35 degrees of Celsius. So let's take the iron nail. I'm going to keep the thermometer away. And now we'll take the iron nail out and we'll see whether we can observe any change in the iron nail. So I'm going to pour out the water. Right, let's see whether there is any change in the iron nail. Right, now in the earlier case, my dear children, this iron nail was a very cleaned iron nail. There wasn't any substance. Now here you can observe when I'm going to scratch this one down by using this glass rod, we can see there are some substance. This substance is like a powder. See? There is a substance around the iron nail and it's like a powder. See? You can see that powder in here. within the liquid. Within the copper sulfate solution, you can observe it. Right. So I'm going to take it to my hand. Let's see. See that powder? See? Now you can observe the iron nail, that shine iron nail within that within this brown color powder. It's a brown color powder. Right? I'm going to use a tissue and I'll show you this powder. See? So it has a brown color. Right? It has a brown color stain. Right? So this powder is copper. Right? In the copper sulfate solution, when I'm going to add the iron nail, the copper is going to deposit, or copper is going to precipitate. These substances, these copper substances, these are not getting mixed with the solution. I mean the liquid. Right? So these substances are getting remained within the solution after the chemical change or the chemical reaction. So these substances which are getting remained within a solution after a chemical reaction is called a precipitation. This is called as a precipitation. So here we can say that new substances have been created. It's because that in the earlier case, when we are dissolving only the copper sulfate, there was no any substance like this. But after adding the iron nail into the system, we can see these brown color stains around the iron nail. And also you could observe the color has reduced. The color of the system also has reduced. And once again, the temperature of the system also rose from 30 degrees to 35 degrees of Celsius. So here we can provide three evidences. Right? Those three evidences are, during the creation of a new substance, we can see a precipitation. So a precipitation means a solid substance like a powder that can be observed in a solution. This solid substance or this powder is suspended on the solution without going into the solution, without dissolving on the solution. So that kind of a thing is called a precipitation. So if a precipitation can be observed in a certain chemical reaction or in a certain chemical change, or in any kind of a change or in any kind of a reaction, if a certain precipitation can be observed after the change, then that change is a chemical change because new substances have been created here. And if the temperature is going to increase, or else vice versa, means if the temperature is going to decrease, or increase, in that kind of a scenario also we can say that a chemical change has occurred in a system. And the third proof is that if the complexion or the color of a system is going to change during some sort of a reaction, or else in some sort of a change. So in that case also we can say that this reaction is a chemical reaction, or this change is a chemical change. So we can provide three evidences by doing this experiment. Those three evidences are, in a chemical change, a precipitation may occur, a temperature change could be observed, change in complexion or change in color can also be observed if there is a chemical reaction. Right. So we'll continue with our lesson once again. Right, my dear children. Now let's see this experiment where we are going to mix this copper sulfate solution, some amount of copper sulfate solution with sodium hydroxide solution. Right. So I'm going to mix these two solutions and to observe what kind of a change is going to occur when I'm going to add these two solutions separately. So let's take a boiling tube and I'm going to add some amount of copper sulfate. Right, my dear children, now this is my copper sulfate solution. Now what I'm going to do is I'm going to add this sodium hydroxide solution into the copper sulfate solution. But I'm not just going to pour it in here to get somewhat clearer observations. I'm going to use a small bit of a dropper, and I'll use the dropper to put this sodium hydroxide into the copper sulfate solution. So I'll use a dropper, right? So this is the dropper. So I'll use the dropper and we'll add drop by drop to check the observations. Check the observations clearly. You can see there is a change in complexion. There is a change in color. See the top part, this part, the color of this part is somewhat darker than the color at below. So I'll add some more. Now you can see it clearly, right? It's very clear to us. There is a light blue color, not that much darker blue, but somewhat of a light blue color precipitation. So precipitation means here you can observe, see, this is a type of a solid. It's not getting mixed. See, type of a solid. You can see it on the wall also. A type of a solid that not getting mixed or not getting dissolved within the solution. It not getting mixed with the solution because it is a precipitation. So when adding sodium hydroxide to a copper sulfate solution, we can observe a light blue color precipitation. So like in the previous activity, here a precipitation has occurred. So if a precipitation is going to occur, means that this change or this reaction is a chemical reaction or else a chemical change. Right, my dear children, now this is our next experiment to observe what are the evidences that we can provide during a chemical change. So here I have a zinc plate. This is zinc. Zinc is a type of a metal. So now I have separated a small piece of a zinc. See, a small piece of zinc. And now in my left hand side on the beaker with me, I have somewhat diluted sulfuric acid. Okay, so this is diluted sulfuric acid and this is the piece of zinc. Now what I'm going to do is I'm going to add this zinc piece into the diluted sulfuric acid. So we'll see what are the observations that we can get from the experiment. So to get the observations more clear, I'm going to use a boiling tube. So I'll add some sulfuric acid. Then gently we'll add the zinc and let's see what are the observations. Right, my dear children, now after passing few seconds, you can observe the system is evaporating gas bubbles much faster. See? So the system is evaporating gas bubbles much faster right now. You can observe it very clearly. So, see? My dear children, to get observations more clearly, I am going to use a black color background. See? So when I'm using this black color background, you can observe the gas bubbles very clearly. Now the gas which is getting emitted in this situation is hydrogen gas, right? So this is another type of an evidence. Here we can say that new substances has got created. New substance has got created and that new substance is hydrogen gas. So in the next grades we'll observe how to identify this hydrogen gas. But you could clearly observe that some amount of gas bubbles are going to emit in this system. So means that we can say that in this system we can conclude new substances has got created. So the evidence that we can provide in this system is that evolution of gas bubbles or emission of a gas is going to occur in a system when mixing two substances or two or more substances, can be more substances. So when mixing two or more substances, if an emission of gas is going to occur, then within that system a chemical change has occurred. That's why the gases are going to emit. So emission of gas is a new substance or it is a new material. So here this experiment shows that formation of gas bubbles and formation of gas bubbles conclude that this system undergoes in a chemical reaction. Right, so we'll head on to the classroom and we'll identify what are the changes or what are the new things, what are the evidences that we can provide if there is a chemical reaction. Right, my dear children, now we are about to conduct this activity. So in this activity, I have set up my apparatus. So I have used a stand, and by using a thread and a small bit of a string, right, I have created this setup. At the two ends of the strings, I have created two balls of iron wool, and these iron wool are fixed to the two ends of the string. See, these are iron wool, right? Now what I'm going to do is I'm going to ignite one end by using this spirit lamp, and you can observe right now you can observe the string is in a horizontal position and it is well balanced. Means that we can say mass of this end is equal to the mass of other end. That's why it is kept in a balanced situation like this. Right, so now what I'm going to do is, so you can see it's in a horizontal position. Now what I'm going to do is I'm going to heat this up. I'll hold the string and I will heat this thing up somewhat. So here you can observe the iron wool is going to give out some kind of a red color, and it's getting burned with a red color. Right, now let's see what has happened to the balance of the system. Now here you can observe this end, it has some kind of a black color, brownish black color. You can see it very clearly, and this end, it has a shiny nature. It's because that this end, after I'm going to burn this end, after burning this end, now this end has iron oxide. In the earlier case also I told you that if I'm going to burn something, oxygen is getting reacted with the substance. So due to that, the color of this one has got changed. This end, we can observe iron oxide. And in here, this end, Here this end you can observe it has a shiny surface, still has a shiny surface other than the other end. And if you check the balance of this one, now you can see it's somewhat slanted to the other side. Somewhat slanted, not that much of a one, but it's got somewhat slanted to the end which has got burned. So in this case, we can say that after the burning, mass of this iron wool has got increased. That's why this rod is not in a balanced horizontal situation. So my dear children, in the earlier activity, we discussed that now during the burning of iron wool, mass has got increased, right? So now I am about to conduct another activity to see whether there is a change in the mass during a chemical reaction or during a chemical change or not. So I have these materials. First of all, in here I have a balance. This is a digital balance, right? And it is very sensitive. We can measure up to 2 decimal places, and here you can observe it's printed grams. It's been printed as grams, G. So here the mass is given from grams. Very sensitive digital balance. So on the balance there is a petri dish, and you can observe now the scale at 0. Now the scale is at 0. So now what I'm going to do is I'm going to take a boiling tube and I'm going to insert some, see, these are matchsticks, and I have removed the tail of it and I have only the head of it, the burning part. So what I'm going to do is now I'm going to put these heads of the matchsticks into the boiling tube. Now I'm going to measure the mass of this system like this. By placing it very steadily on the digital balance, I'm going to measure the mass of it. So here it's been printed on the screen 29.60. So the total mass, the entire mass of this boiling tube which contains the matchsticks heads is equal to 29.61, right? We'll get an accurate answer. Okay, 29.61 is the answer. Okay, right, 29.62. See, it's very sensitive. That's why I told you it's very sensitive. So we have to keep all the systems very steady. Otherwise the mass will reduce or increase. We can't get a clear observation. So final value of the digital balance is now 29.62. 29.62 grams. You can observe it on the screen here. It's been printed 29.62, right? Okay, so now I'm going to take the boiling tube away, and what I'm going to do is I'm going to heat this up and burn all the matchsticks inside the boiling tube. So and let's heat up. Right. So now what I'm going to do is I'm going to take away the boiling tube. Here you can see a smoke is getting emitted. See, a smoke is getting emitted means that a chemical change has occurred in this system. Now let's measure the mass of the system right now. So in the earlier case, my dear children, you could observe 29.62. 29.62 was the answer. But after the chemical reaction, I can get a clear observation. It's been reduced to 29.53. Means that some amount of mass has been reduced during this chemical reaction or during this chemical change. Some amount has been reduced. So in the early activity, some amount has been increased, and in this activity, some amount has been reduced. From 29.62 to it has dropped 29.52. Here you can observe 29.52. This is the final answer, 5352. Okay. So let's see, or let's once again let's head on to the classroom and let's write down the conclusion and the observation of our experiment. Right, my dear children? Now, in the earlier two situations, we conducted, or we did the chemical change, we did a chemical reaction in an open environment. Means that particles can freely enter to the system or freely enter to our unit, right? And particles which is contained inside the chemical reaction, whatever the particle which is getting newly produced, can exit through the system, right? So that kind of a system is the one which is referred as an open system. So in the earlier two cases, we conducted open system chemical reactions. Okay, we did chemical reactions in an open system. So when I'm burning matchsticks, you could observe that the smoke is getting emitted from the system, from that boiling tube. Now in this activity, we are going to enclose the entire system, and now let's identify whether there is a change in the mass of the materials or not after the chemical reaction. So once again, I have these materials: boiling tube, a balance, a digital balance like in the previous cases, a spirit lamp, some matchsticks. Once again, I have used the heads of it, right? And a balloon to enclose the top of the, or to enclose the boiling tube. I have a balloon. So these are the materials that I have, and I'm going to conduct the experiment right now. So let's see. First, I'm going to take the boiling tube, and I'm going to insert these matchsticks into the boiling tube. In the next step, so I'll remove these things. In the next step, I'm going to insert this balloon on the boiling tube like this, so that the gases will not enter to our system, or after burning these things, the gases created inside the system will not go outside also. So I have enclosed it. So now I am going to place it on the balance, and let's measure the mass of the system. So let's measure the mass of the system. We'll keep it somewhat steady to get a clear answer, to get a clear value. So here you can observe the digital balance is printed. The value is being printed as 32.57. So my value is 32.57, right? So remember the number, children, 32.57. That's the mass of this system. Now I'm going to take it out, and I'm going to heat up this boiling tube. So when you know that when I'm going to heat this boiling tube, the matchsticks matchsticks heads inside the boiling tube will burn out and they will undergo in a chemical reaction, right? So I'll heat it by using the spirit lamp in here. Right. Now, my dear children, I'm going to measure. So I'll enclose this thing. Now, my dear children, I'm going to measure the mass of it. Right, my dear children. Now, I have placed it in here. Here you can see the balloon has been inflated. See, the balloon has been inflated. All the smoke coming out from the reaction is being filled into the balloon, and the amount, see the amount 32.57. So the amount or the mass haven't changed in this time. Mass haven't changed in this time. So now why the mass haven't changed in this time? Because the gas or the whatever the smoke which is coming out from the system now is being filled to the balloon. So there is no mass which is getting released to the system or released out from the system to our environment. No mass. You know that gases or smoke is a type of a material. It's a type of a matter. Almost all the matter, 100% of matter in our environment, they have a mass. This digital balance is very sensitive. So even we can measure the masses of the gases as well. So when the system is opened, the smoke which is coming out has a mass. So that's why the reduction of mass occurred in the earlier case. Now that gas is being filled into the balloon here. So therefore, there is no loss in the mass. There is no loss in the mass because all the gases which is emitting to the environment, now we have collected it to the balloon. So in a closed system, there is no change in the mass, right? So we'll conduct another activity to ensure that our result is correct. Right, my dear children? Now, this is the second activity to see whether there is a change in the mass during a chemical reaction in a closed system. So here I have once again lead nitrate. I have lead nitrate with me, right? I have lead nitrate with me, and so I have poured some lead nitrate into the petri dish. So this is lead nitrate, right? And this is in the ignition tube. Here you can observe in the ignition tube sodium chloride. So now what I'm going to do is, first of all, I'm going to add some water, and by using this wash bottle and make a solution of sodium chloride, right? Okay, I'll shake and dissolve sodium chloride in the ignition tube. Right, now by using another flask, I'm going to add some lead nitrate into it. I will use this spoon to get the lead nitrate into the flask. Right. Now let's add some water and make a solution. You have to dissolve it very well inside this container. So we'll dissolve it. So the lead nitrate solution. So I have dissolved lead nitrate in this flask by using water, and I've made a lead nitrate solution here. So now I'm going to keep it here. Then I'm going to take the earlier ignition tube which has sodium chloride. So here you can observe there is some amount of sodium chloride at the bottom still. So I'll shake somewhat. Right. So here you can see in this within this ignition tube there is sodium chloride, and you can see the solution very clearly. I have added somewhat more water to dissolve all the sodium chloride in the ignition tube. Now I'm going to gently insert this thing into this system, very gently, and I'm going to keep it like this kind of a position. Right. So I'm going to keep it in this kind of a position, and I'm going to insert the cork very well so that it would seal up. Right. So make sure to seal the system very well, because I told you that it should be a enclosed system. It should be a closed system. So this is my system now. Ignition tube which contains sodium chloride, and the other vessel, the larger vessel, which contains lead nitrate. Now I'm going to place it on the balance to measure the entire mass of it. So my final value is 175.28. 175.28. That's my final value, 175.28. Right. Now I'm going to take this one up, and I'm going to mix the sodium chloride with the solution here. Right. 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 So here you can see it very clearly. There is a chemical change and there is a precipitation inside the ignition tube. Now I am going to place it on the balance and we'll see whether there is a change or not. So my dear children, once again you can observe, even though the chemical reaction has occurred within this system, you can see that there is a precipitation inside the ignition tube. But the mass of the system haven't changed at all. Mass of the system is still at 175.28. So we can finally conclude that then in a closed system, there is no change in the mass even after a chemical change. So here the mass is preserved in a closed system during a chemical change. So this law of preserving mass is called as law of preservation of mass, or else this thing is referred as the law of preservation of mass. So this is how we can say that a closed system do not waste or do not in a closed system there is no change in the mass. So this is the final conclusion that we can arrive from these two experiments. Right then, so we'll head on to the classroom once again and we'll conduct about further things related to this preservation of masses. Right, my dear children, now in this activity we'll be observing ignition temperature of several substances. Now I have a metallic plate with me. I'm going to heat it down, so therefore I need to get a metallic plate. So I have a metallic plate here, and within the metallic plate you can observe there are several substances, right? So these are the substances which are on the metallic plate, right? So what are the substances? Here you can see a small piece of a paper, a piece of a cotton wool, right? A piece of a magnesium, some amount of sugar crystals, then a matchstick head. It's a piece of matchstick. Actually it is a head of the matchstick, which is in here, right? Head of a matchstick, and a piece of sulfur. This yellow color substance, a piece of sulfur, right? Sulfur. So sulfur, matchstick head, piece of paper, cotton wool, piece of magnesium, some amount of sugar crystals, right? So now I'm going to fix this metal plate containing these substances on the stand, right? So I'll fix it on the stand like this. Right, children, now let's heat up this system and we'll observe which material will ignite first and which material will ignite last. Okay, so I'll use the spirit lamp to heat up the system given here. So place it in here at the middle so that the heat would distribute evenly throughout the system. So check the order of ignition. So you could observe that matchstick got ignited quickly. Then after that the piece of sulfur, then the cotton wool, then that sugar crystals, the piece of paper. The magnesium piece is still in contact, right? There's no change in the magnesium piece still. So magnesium piece is the remaining one in this experiment. So you can see that matchstick got ignited quickly. Then after that the piece of sulfur, then the cotton wool, then sugar, then the piece of paper and sugar. Then after that the final one is, which is remained still in the metal plate, which is the piece of magnesium, right? So from this activity we can say that the materials which are going to ignite very quickly, they have less ignition temperature. So ignition temperature is the temperature at which a given substance start to burn, right? So matchsticks got burned very quickly when heat is applied. So matchsticks has the very less amount of ignition temperature, right? So if you take the piece of magnesium has the highest amount of ignition temperature, right? Still the magnesium piece is not getting burned at all. So magnesium piece still it is not getting burned, right? It is still in the metallic plate, and there is no any difference in the color as well. So this is the order of ignition then, right? So we can say that the materials that has the highest ignition temperature, materials that has the highest ignition temperature will ignite at the last, right? Materials which has the lowest ignition temperature will ignite first, right? So this is how to identify the ignition temperature in certain materials, right? Then so we'll head on to the classroom once again and we'll write down our observations and conclusions from this activity, right, my dear children? Now in this activity we'll be studying about the products created during a combustion of a fuel, right? Especially here we are discussing about during a combustion of a candle like this. Okay, what are the products which are getting created? So I have prepared a certain apparatus here with several materials. So one by one I'll let you know what are these things. So here first of all we'll be needing a stand. So this stand is being used to fix all the other materials firmly, like in this setup. Okay, so then we'll be needing a funnel, right? That funnel is being used to direct the smoke which is getting emitted from the candle towards the system which is in here. Okay, so the delivery tube which allows to flow gas or the product which is coming from the candle. Then here you can observe a U-shaped tube. This is a U-shaped tube. It's been like drawn into a shape of a U, right? And the smoke which is coming from the delivery tube going through this arm of the U tube and traveling to the other arm as per to the apparatus. Then at the two ends I have stopper it, right? I have applied several stoppers at the two ends so that the gas which is coming from here is going through there to the next arm, and it is getting exit from the nozzle in here towards the other vessel which is on here. Okay, so inside the U tube here you can observe there is certain chemical. In here there is one certain chemical, right? This chemical is copper sulfate. This chemical is copper sulfate. Especially this copper sulfate, this type of copper sulfate is called as anhydrous copper sulfate. Anhydrous copper sulfate. Usually if you take copper sulfate, it will be like this. Copper sulfate, usually it will be like this. See, this is usual copper sulfate. It's in blue color. See, it's in blue color, right? Usual copper sulfate. This is hydrous. Hydrous means it contains or it absorbs water. So this is hydrous copper sulfate. So anhydrous copper sulfate means after heating these copper sulfate, you can take some amount of blue color copper sulfate and you can heat it. So when you heat copper sulfate, the water vapor which is absorbed to the copper sulfate crystals will get evaporated, and the copper sulfate crystals will turn into a white color like this, which is in the U tube. Okay, so this is anhydrous copper sulfate, okay, which I have prepared by heating up hydrous copper sulfate. Okay, so when there is water vapor, when water vapor is getting absorbed with copper sulfate, the color of this copper sulfate is getting into once again blue color, the original color of copper sulfate. Okay, but in order to do that, it should be come in contact with water vapor, and those water vapor should absorb into the copper sulfate crystals. Right then, so then finally the smoke coming from the candle goes through this delivery tube to the DU tube. Then after that, from the second delivery tube towards this vessel. So this vessel contains lime water solution. You can observe it is colorless, right? The lime water solution, it is colorless, do not contain any kind of a color, right? So it's a colorless lime water solution. So the smoke which is coming out from the candle passes through the candle towards the delivery tube, towards the U tube, goes through the copper sulfate crystals, anhydrous copper sulfate crystals, comes with the other arm and goes through the delivery tube here and comes down and travel through, or it's getting bubbled through the lime water solution, right? That's how these apparatus work. But there is a certain thing, we have to connect this thing to an aspirator like this. So I have to, like, you know, we have to suck the air particles out of this system so that the smoke will come directly towards this delivery tube, towards the U tube. Otherwise, if the flame of the candle is going here and there, we can't get a direct observation clearly. So therefore, I have connected this system to an aspirator, right? So when the aspirator is working, the gas inside this system is getting sucked out from the system. So therefore, the flame or the products created in the candle is going to emit only towards the U tube and the other system. So it's important to connect this aspirator, otherwise the flame will go here and there and the products which are getting created will not flow towards these materials. So getting observation would be quite difficult. So therefore, aspirator is providing a time, like enough time to get a good observation from the system or from the experiment. So we'll conduct the experiment and we'll see what are our observations within this setup. Right. So I'll ignite the candle first. Then we'll see what's going to happen. So first of all, I'll use the candle and fix it to the wall like this. Right then, so I have prepared the system right now. So we'll operate the aspirator and keep the candle flame somewhat steadily so that the smoke is coming out from here. So that the smoke which is coming out from the candle is going towards the system to my right hand side. Okay. Right, so we'll operate the aspirator then. Right, so here you can see that the aspirator is working now. So the candle flame or the product which is getting created is coming towards the anhydrous copper sulfate crystals. You can see it. So we have to give it somewhat time, right? So that the products which are getting created during the combustion of candle to come in contact with the chemicals. So here you can observe now gradually the color of lime water solution is getting converted into a milky white color. Can you see? Now when I was conducting the experiment, so when initially this chemical was in the system, the color was like the color of water. Now it's been turned into a milky white color. Here you can observe it, see. And here also we can see that gradually the copper sulfate crystals are also getting converted into light blue color. See, gradually it's getting converted into light blue color. So we'll give out some more time and let's observe. Right, my dear children, now here you can observe our observations very clearly now. So I have let it for some time and now we can observe pretty much good or pretty much clearer observations. So here you can see copper sulfate solution. So I'll stop this aspirator, right? So I'll stop it now. Okay. So now let's see. First of all, I'll put off the flame in the candle, right? So now gently I am going to remove this setup to show the color of copper sulfate. Right. Okay then. So here you can observe the color of copper sulfate in here right now. See, the color of copper sulfate solution, it has converted into a blue color, right? We can observe it. It has converted into a blue color. You can see it very clearly. It's been converted into blue color. Means like this copper sulfate, I'll take the actual copper sulfate. So like this, it's been converted into blue color. So original color of the copper sulfate was white in color, white color. So when white color copper sulfate, white color copper sulfate means anhydrous copper sulfate. White color means anhydrous. There is no water. So when white color anhydrous copper sulfate come in contact with water vapor or water, it's getting converted into blue color like this. So this is called as hydrous copper sulfate. So due to that gas which is coming out from the candle containing water vapor, this copper sulfate has got changed into blue color once again, right? So we can conclude from this experiment, from this observation, we can conclude that during the burning of candle wax, water vapor is getting emitted. That's why the anhydrous copper sulfate has got into a different color which is the blue color. Now I'm going to keep it. So I'm going to ask you a simple question. Why do we need to keep a water trough like this? So you saw that I kept the water trough like this and dipped it inside the water trough, and I have fixed it to the two delivery tubes by keeping copper sulfate within the water like this. So what's the reason of dipping this U-tube inside the water trough? It's because the vapor which is coming out from the system is getting cooled down due to the water which is contained in the trough, right? It's getting condensed. Water vapor which is coming out from the delivery tube is getting condensed due to less amount of temperature within the water trough. So to cool the vapor or to cool the products which are coming out from the candle, we can use this water trough, right? Okay. So now let's come on to the other vessel where we use the colorless lime water, right? So here you can observe that the colorless lime water has got also a milky color, a milky white color. This is because of carbon dioxide. From grade 6 onwards, you are going to study that. You are being studied from grade 6 onwards. The lime water, colorless lime water, can turn into milky white solution like this with the presence of carbon dioxide gas. So here also you can observe the colorless lime water has got changed into milky white color. That's because of having carbon dioxide. That's because of having carbon dioxide gas. So where did we receive carbon dioxide to the system? We received carbon dioxide to the system by the burning of candle wax. So here, by using this observation, where the color of lime water change. So here, this observation can be used to identify the presence of carbon dioxide gas during the burning of candle wax. So this activity finally concludes. During the burning of fuel, or else during the burning of candle wax, the main products which are getting created are number 1, water vapor, and number 2, carbon dioxide gas. So let's head on to the classroom and we'll write down our observations and conclusions from the activity. Right, my dear children. Now we are about to discuss the areas of a candle. So if you take a candle flame contains several areas, right? So within this activity, we'll be discussing those areas, how to identify those areas in a candle flame. Right now, I have a lighted candle with me, right? So let's identify the areas in this candle. So here, if you take the area around here, right, this area, it's barely visible actually. You can't clearly observe this area which I am pointing. Like a shadow. It's like a shadow. Like a small bit of a shadow is getting emitted from that area, right? It's very barely visible to us. Okay, so that zone is referred as the outer zone of the candle flame. Outer zone. So this area after the outer zone, this area here, you can observe that area which I am pointing in here. This area has a bright color, bright yellow color, this area. So that area is referred as the luminous zone of the candle flame. The luminous zone. Then after that, below the luminous zone, like when you come up to here, this area, within this area, there is a flame, but we can't observe it very clearly. Actually, it has become invisible and it has become transparent too. Transparent means invisible here. You can directly see the black color surface in here to this area, in here, this area, right? You can't observe a flame, but the flame is there. Actually, you can't observe it. It's because that area is invisible to us. The invisible zone. So finally, at the bottom, you can observe the blue color range. Here, you can observe a blue color range in the candle flame. So in a candle flame, these are the main types of areas which we can observe in a candle flame. right? So my dear children, when we are discussing further things related with the candle flame, right, you will be observing, or you will get to know what are the contents of each in these areas, right? So we'll head on to the classroom and let's see what kind of things or what sort of things are contained within the each area of the candle flame. Right, my dear children. Now then, in this activity, we'll be identifying several zones related to a Bunsen flame. So I have a Bunsen burner with me right now. So if you take a Bunsen burner, we can identify these areas, right, or these parts in a Bunsen burner. This base, it helps to fix the Bunsen burner on a tabletop like this, or on a surface to keep the Bunsen burner rigid. We can use this base. So base can be used to keep the Bunsen burner rigid. And after the base, you can observe there is a collar. This collar can be turned here and there. So when turning the collar here and there like this, you can turn it like here and there like this. See, you can observe the change of color in the Bunsen flame. It's because that there is a air pore like in here. So it allows to flow oxygen gas into the Bunsen burner. So you know that to burn any kind of a fuel, we need oxygen. So this is the entrance where oxygen gas is getting entered to the Bunsen burner, right? And you can observe the stem of the Bunsen burner next, right? This is the stem, and with after the stem, you can observe the end of the Bunsen burner. So this is the gas tube which is being connected to LP gas supply. The LP gas coming out from the tube will get burned within the stem like this. So now let's identify the zones in a Bunsen flame. So I'll keep a black color board so that you can clearly observe. Now let's observe what are the areas or what are the zones that we can identify in a Bunsen flame, right? So first of all, if you observe this area, which is the most outer layer. So most outer layer in the Bunsen flame, you can observe the invisible zone, right? Unlike the candle flame, the Bunsen flame has like 99%, up to 99% a blue color, right? Here you can observe like small bit of a yellow color at the end of the Bunsen flame, but most of the areas are in blue color, right? So at the outermost area or outermost zone, you can observe the invisible zone. The invisible zone. Then the zone after it, the second zone, like in here, right? You can observe the light blue area. It's somewhat light blue. If you compare the colors between here and here, this area and this area, right? So here you can observe some kind of a dark blue color, and here you can observe a light blue color. So these two zones are the light blue zone and the dark blue zone, right? So like in the candle flame also, here we can observe an invisible zone or else a non-luminous zone. Then after this light blue area and the darker blue area, in between those two, like in here, you can observe the non-luminous zone. It's not luminous to us. Actually, like it's invisible. Sort of an invisible area can be observed in here, right? In this area. So that is the non-luminous zone. So once again, we'll memorize what are the zones. So in the outermost area, you can observe the invisible zone. Then after that, the light blue zone, the dark blue zone. In the middle, in here, you can observe the non-luminous zone. So in a Bunsen flame, we can observe these 4 areas or these 4 zones very clearly, right? So we'll head on to the classroom and we'll observe what kind of things are contained in each of these zones. Right, my dear children? Now in this activity, we'll be identifying the factors which are essential for the rusting of iron. Especially in this activity, we'll be observing whether air is necessary for the rusting of iron, right? So I have these materials with me. So I'm going to conduct the activity. So let's see first of all what are these materials. So I have first of all a forceps to handle the boiling tubes, right? Then after that, several boiling tubes. Here I have 3 boiling tubes, 1, 2 and 3. Some water. Then this is coconut oil, right? Coconut oil. And some cleaned iron nails. Here you can observe there is no rust in these iron nails. Okay. I have 3 iron nails separately for each boiling tube. So these are very cleaned and there is no rust at all. See, you can observe it. These things are very clean and there is no rust at all. Right. And I have a spirit lamp here with me. So I'm using this spirit lamp to boil water. Okay. So let's see how to conduct the activity then. So first of all, I'm going to do is I'm going to insert 1 iron nail each like this for the 3 test tubes separately. Number 3, right? Then I'm going to take some amount of water and just add this cool water. This is cool water, normal cool water, tap water. I'm going to insert this normal cool water into 1 test tube so that it covers entirely like this. So that the iron nail is getting covered entirely like this. Okay. So I'll place it in here. Number 1. Then I'm going to use the second test tube, this one. Once again, I'm going to put some amount of normal water like this. Then for this, I'll be inserting some amount of coconut oil, right? So I'll place the test tube like this and I am going to insert some amount of coconut oil into this solution, right? So here you can observe that after inserting coconut oil up to a certain limit, the coconut oil layer and the water layer is getting separated like this, right? Okay, now the number 3, third boiling tube. In the third boiling tube, there is an iron nail, you can see it. So I'm going to insert water to cover up the iron nail. Then I'm going to heat this boiling tube very well until the water boils. till I'll keep this system somewhat away like this. I'm going to use my forceps then, and I'm going to take this boiling tube which contains normal water, and I'm going to heat it down until water is going to boil, right? So what's the purpose of boiling water? Purpose of boiling water is that we need to expel all the gases which are dissolved already inside the normal water. You know that gases like oxygen, carbon dioxide are slightly getting dissolved inside water. So to expel all the gases contained in water, I am going to boil it very well. So you know that when you are boiling water, the gases which are already dissolved inside the water is going to evaporate. So let's boil water and evaporate all the gases inside the system. Right. So keep it in here. Let's light up the spirit lamp and we'll boil in tube until the water is going to boil and evaporate all the gases in it. So give it some time to boil water. It's important to boil the water very well to evaporate all the gases dissolved in it. So already you can see that the bubbles are getting formed inside water. Those bubbles are the air particles or gases which are already dissolved inside the water. So I'll use this black color surface. Here you can observe. See, the bubbles are right. Now it has boiled very well. So I'll remove it now. Now let's keep it for some amount of time. Now we'll add the coconut oil into it. Okay. A good layer of coconut oil. Right. So we used boiled water in this setup. Okay. And I have added coconut oil as well. So what's the purpose of adding coconut oil for these boiling tubes? You know that these test tubes or these boiling tubes are exposed to normal air. It's in our normal environment, no? And you already know that gases are going to dissolve within normal water. So if you take this boiling tube, it do not have any coconut oil layers. So here this one is exposed to the normal air in normal atmosphere. But this one, it's also been exposed to the normal atmosphere. But when you're adding coconut oil into it, right? When you're adding coconut oil into it, the gases which are at the atmosphere is not getting in contact with water at the bottom. So the gases or the atmospheric gases will not get dissolved inside the water, right? So it inhibits the dissolving of gases, atmospheric gases in normal water, right? So the purpose of adding coconut oil is to avoid the dissolving of gases within water. Right, now let's insert this thing into the test tube container, right, like this. So here you can see, if you take this one has the boiled water where we use the single stand, and this one, it contains cool water or normal water, right, in the other stand. Now we need to keep this setup for about 2 to 3 days to get our observations. So we'll keep these set up in a different place so that they would have some time to process. And after 2-3 days, we'll see what are our observations. Right, my dear children? Now, I have kept this system for about several days. So now I am about to see what are the changes that occurred in each of the iron nail. So first of all, I am going to take the boiling tube that contains normal water. If you check this setup, you can see clearly the color of water has already got changed. Initially it had a color, it haven't got any kind of a color. It was colorless. Now it shows some amount of a yellow color, light yellow color. So let's see what has happened to the iron nail. So I'll put this solution into the Petri dish, and now I'm going to take the iron nail out. So if you observe this iron nail, you can see iron nail has rust, and it has rusted very well. See, it has rust all around the surface, right? So it has rust very well, right? So I'll keep this iron nail by keeping it on the Petri dish so that you can observe very clearly. This is the first one which contains normal water. Okay. Now I'm going to use the Petri dish, the boiling tube which contains, now this is the boiling tube which contains normal water plus some amount of coconut oil, right? So I'm going to pour it down to this Petri dish once again to observe the color change. So in here, in this one you can observe there is rust, but up to a certain limit, up to a certain extent. Not that much rust. Okay, there is not that much rust rather than the previous one. It has rust, but up to a certain level only. We can't find rust all around the surface like the previous one. Okay, so I'll keep it in here. Then I'm going to use the third and the final boiling tube. So I'll remove this one. This was the 2 boiling tube which contains normal water, right? So this is the one which contains then the boiled water. So I'm going to take the Petri dish, third one, and insert this solution into it, and we'll see what has happened to the iron nail. So if you check this iron nail, you can see there is no rust at all. There is no rust at all, right? See, there is no rust. Right. So I'm going to keep it over here. So I'll use a tissue paper, right, and place each of these iron nails so that you can observe it very clearly. Right. The first one, this one contained normal water. There is no coconut oil in it. So this is the first one that contained normal water, right? Check how the iron nail has rust. Normal water. Second one, normal water plus some amount of coconut oil. Normal water plus some amount of coconut oil. Right? Number 3, the third and final one, boiled water plus coconut oil. Right. So these are the 3 iron nails. So we'll compare the rust in it. Normal water only, it has got rust all around the surface. Normal water plus some amount of coconut oil. To avoid the contact of air particles, we add coconut oil. So coconut oil plus normal water. There is rust, but up to a certain limit, right? Not that much rust like this, but up to certain limit it has rust, right? Now the third one, the final one, boiled water plus coconut oil. There is no rust at all. You can observe there is no rust at all. See? So these are the observations from this experiment. Right? So my dear children, let's head on to the classroom once again and we'll write down our observations which we took, and let's see what is the explanation for these kinds of observations. Right, my dear children? So in this activity we'll be investigating the next factor which is important for the rusting of iron. Right? So here we'll be examining the necessity of water vapor or moisture for the rusting of iron. So first of all, I have a cork, and by using this sandpaper, first of all I have stretched the surfaces of the iron nails very well and I have cleaned them. Okay, so you can observe there is no rust in it. So I'll remove the iron nail and I'll show it to you. There is no rust in these iron nails. Right? So there is no rust. See, these are very cleaned. These iron nails are very clean. There is no rust at all. See, this one also, there is no rust at all. I have cleaned them very well by using the sandpaper with me. Right. So once again I'll insert. Okay, so I'll keep it in here. Then I have with me a substance. This is called as calcium chloride. This is calcium chloride crystals. Specialty in calcium chloride is that calcium chloride can absorb water vapor in the atmosphere. Okay, so calcium chloride can absorb the water vapor in the atmosphere. So first of all, I'm going to use this calcium chloride and I'm going to insert this calcium chloride into our boiling tube. Right. So here we go then. I have inserted calcium chloride into the boiling tube. Then after that, what I'm going to do is I'm going to stopper it very well with this that has iron nails. See, cleaned iron nails. Okay, now I'm going to stopper it using this cork. So I'll insert to here and I'm going to insert it very well like this. Okay children, now this is our setup. So inside Inside the boiling tube, there are some parts of iron nails, and outside the test tube also there are some parts of iron nails. Inside the test tube, you can observe calcium chloride. So we'll keep it for some days. We have to keep the system for about 2 to 3 days. And after 2 to 3 days, we'll observe what has happened to iron nails. So we'll leave it like this, and after 2 or 3 days, we'll observe what has happened with the iron nails then. Right, my dear children, so I kept this system for about 5 days, right? Then here is my system right now. Okay, observe the system very clearly and check what has happened to the iron nails. You can observe clearly the top part has some amount of rust, right? The top part of the iron nail, which is getting contacted with the normal atmosphere, it has some amount of rust. If you check the part which is below means which is inside the boiling tube, in this part there is no rust at all, right? There is no rust at all, right? You can see it very clearly. These parts, the topper parts contain rust, but the below parts, which is inside the boiling tube, these areas do not contain any rust. These areas do not contain any rust, but these areas contain rust. Reason for this is, you know that, and I told you earlier also, calcium chloride can absorb water vapor. Calcium chloride can absorb water vapor or moisture. So when I'm going to insert the stopper, some amount of water vapor is getting trapped inside the boiling tube. So that water vapor is getting absorbed by calcium chloride. So inside the boiling tube, there is no water vapor at all, right? But when you take outside, in outside there is normal, if you take outside this part, there is normal air in outside. In normal air or in atmospheric air, you know that there are some amount of water vapor. So these areas are getting contact with water vapor rapidly. But the area below or area which is inside the boiling tube do not get in contact with water vapor, right? The part of the iron nail which is located below the boiling tube do not get in contact with water vapor, because all the water vapor inside the boiling tube has already got absorbed by calcium chloride crystals. See, in here you can observe calcium chloride crystals. So calcium chloride crystals can absorb all the water vapor inside the boiling tube. So within this activity, or when conducting this activity, it's obvious to us that water vapor is really important for the process of rusting. If there was water vapor inside the boiling tube as well, then in that kind of a case, the inside part also will contain some amount of rust. But here, the inside part do not contain any rust. Means that water vapor is really necessary for the process of rusting. But when you compare the outside part means the area which is exposed to the normal atmospheric conditions. In normal atmosphere, there is plenty of water vapor. So this area is getting contacted with water vapor rapidly. So these areas or these iron nails will get rust very quickly as they have plenty of water vapor. So this concludes that water vapor is really important for the rusting process. Right, my dear children. Now in the earlier activity, we discussed that air is necessary for the rusting process. You know that atmospheric air in the early activity discussed, air is necessary for the rusting process of iron. But you know that if you take air particles, the normal air particles within our atmosphere, it contains several components, right? Contains several components like oxygen, carbon dioxide, hydrogen, nitrogen, right? So like that way, there are several components contained in normal atmospheric air. So we know that air is necessary for the rusting process, but we don't know which factor of air is necessary for the rusting process. So in this activity, we'll be investigating what factor of air particles is responsible for the rusting process. So to conduct this activity, I have prepared a setup by using two stands here, a water trough, and with several boiling tubes. Okay. So first and foremost, these boiling tubes should be identical to each other in all aspects. Okay, I mean their radius should be equal to each other like this. Their width should be equal to each other, and they should be in a same volume for sure. Okay, because at the end we'll be comparing, right? At the end we'll be comparing our observations one relative to another. So in that case, to check whether we have got the necessary observations, we need to make sure that these boiling tubes are in the same dimensions, right? So now I have two boiling tubes with same dimensions. First of all, then I'm going to use some amount of iron powder or iron fillings. Iron powder or iron fillings. Right, now first of all, what I'm going to do is I'm going to insert this iron powder. Right, I'm going to insert this iron powder into this test tube, my dear children. Right, so I'll use a small bit of a spoon. Then what I'm going to do is I'm going to insert this iron powder into our boiling tube like this. We need to insert the iron powder up to some extent. Right, okay, so we'll add some more iron powder into the system. Right, that's enough. So I have inserted some amount of iron powder into the first boiling tube. Then we need to place this boiling tube inverted in this trough, water trough. We need to place it inward, right? So I can't directly keep it inverted in the trough, no, because iron powder will fall to the water trough. So to avoid falling iron powder into the water trough, I'm going to insert some amount of cotton wool. I'm going to take some amount of cotton wool and I'm going to place it within the boiling tube so that the iron powder will not fall into the water trough. So you have to take some amount you have to take some amount of cotton wool, otherwise the iron powder will fall into the water trough. Right, that's enough. So I'll dip it in water. Right, now let's insert this thing. I'll use a glass rod to insert this firmly into the boiling tube. Right. So gradually I am inserting this thing to the boiling tube like this. Okay. Right. So this is our first setup then. Right. This is our first setup. Now I'm going to place it in here. I'm going to take the second test tube and I'm just going to take this cotton wool. Then once again, like in the previous one, I'm going to insert it in water like this. I'm going to wet it down to a certain extent. Then I'm going to insert this cotton wool to the boiling tube once again. Okay. Here we need to provide the same amount of volumes to the both boiling tubes. Remember it. That's why we are inserting the second cotton wool layer to the other boiling tube. Okay, so let's insert it. Right, so let's compare with the other one. Right, the second one, this one should go somewhat further down. Right, just slightly down, then we can continue with the next step. Yep. Okay, now these are our two boiling tubes then. Keep it in here so that you can see it very clearly. Right, our two boiling tubes. So the first boiling tube, this one, this boiling tube contains a cotton wool and some amount of iron fillings or iron powder which is trapped inside the boiling tube. In the second one, there is only some amount of cotton wool which is same as the amount of cotton wool which I have inserted to the first one. Now what I'm going to do is I'm going to insert these two boiling tubes. Right, okay, make it into an inverted like this. Now let's insert this thing into our water trough. So remember, when you are fixing these boiling tubes inside the water trough, both the boiling tubes should be in a same level. Both of these boiling tubes should be in the same level, my dear children. Okay, both of them should be in the same level. Right, remember it. So we'll insert the second one also. So by looking at this level, I am going to insert it. Right, so I have fixed both the boiling tubes up to a same level. right? You can observe that both the boiling tubes are in the same level right now. So now we'll need to keep this system for about few days. And we need to observe what has happened to these iron fillings. And is there any other observation within the boiling tube of this one or this one? Actually, we can get some observations only in this one because this is the one which contains iron fillings, right? So what is the purpose of using this second boiling tube? It's like this. Now, when there is some sort of a change which is going to occur inside the first boiling tube, if some amount of gases are getting absorbed during the process of rusting, to fill that gap, some amount of water will rise through the boiling tube. But we don't know how much is the volume of it. To compare and get an idea about the volume which has risen up, we have used this second boiling tube. We can compare up to how much of a volume has the water been risen up through the boiling tube. After the rusting process starts, some amount of gases are getting absorbed by the rusting process. Means that some amount of water should rise up through the boiling tube. If I'm going to keep this setup in the same way, I won't be able to compare my observations very clearly. So what I'm going to do is, I'm going to apply some amount of a color, right? Some amount of a coloring for this water throw. So after adding coloring, you can observe the water, two levels of the water very clearly, right? So if I'm going to keep it in the same way, I won't be able to get more clear observations. So there might be a possibility where our observation would get faulty. So what I'm going to do is, I'm going to add some amount of colored water to this setup to get my observations more clearly, right? So we'll add some colored water. And gently, very gently, we'll mix it. Right. Now after the rusting process starts, you can observe the clear level of the water after rust have been created on the iron fillings. So what I'm going to do is, right now I'm going to keep this system for about 2 to 3 days. Then after that, I'm going to observe what is going to happen. Right, my dear children, now you can clearly observe what has happened to our setup. After adding colored water, we can get the necessary observations more clearly. This is our first test tube. This is our second test tube, which used to compare the volume of water. So here you can see from this level, this is our normal water level. From this level to this much of a level, water has risen up. So from here to here, let's compare by using this boiling tube. We'll compare how much amount of water has risen up in this boiling tube. You don't need to get more accurate answer in this thing, right? Just get a rough value, right? This is to get some idea. So just get a rough value. You don't need to take more accurate values in this thing, right? So we'll compare with this thing. How much is the how much times water has risen up. So here to here, and this smaller part which the water has risen up. So we'll see how many parts are there. Here to here, 1, 2, 3, 4 and 5. Once again about, see, 1, 2, 3, 4 and 5. Roughly there are about 5 parts in the entire volume here to here. Right? From this water level to top of the boiling tube, there are like 5 parts. Right? There are like 5 parts. So out of those 5 parts, 1 part is colored water. Now this is the part which water has risen up. So this part which the water has raised up is exactly 1/5 of this entire volume here to here. It's not exactly 1/5, right? But up to a certain extent, roughly, it's around 1/5. 1/5 of the total volume from here to here. So the amount of water which has risen up is about 1/5 of the total volume of the container. Right? So that is our conclusion from this activity. Water has risen up about 1/5 of the entire volume in the boiling tube. Okay, about 1/5 of the entire volume we can observe colored water. That's the amount of colored water which has risen up in this activity. Now what I'm going to do is I'm going to check what has happened to iron powder or iron fillings inside the boiling tube. So now what I'm going to do is I'm going to remove this system gently. And I am going to take out the boiling tube and I'll keep the stand and take this petri dish. Now I'm going to take this cotton wool and let's observe what has happened with the iron powder. Okay. Right, so I can't take entire iron powder because you can remember I added some amount of water into this cotton wool. So here let's see what has happened to iron powder. Right, so iron powder has some amount of rust. Iron powder has some amount of rust. Okay, so I'll use this white color. I'll use a white color background to show it to you. I'll use a tissue paper, right? So I'll use a tissue paper. Right, now I'm going to use this iron powder and rub against with this white color paper so that you can see very clear image. Okay, so we'll see. So I have rubbed it against the paper here. You can see there is a brownish yellow color stain. There is a brownish yellow color stain. See, there is a brownish yellow color stain. Means that this iron powder has rust. Right? It has rust. That's why it contains a brown color or brownish yellow color stain. Right? So, what is our conclusion from this activity then? You know that 20% of our atmosphere contains oxygen. About 20%, not exactly 20%, about 20% from our atmospheric air, there is oxygen. With 1/5 of a container, or when you convert 1/5 into a percentage, that's also about 20%. It is exactly 20%. Right? So the amount of colored water which has risen up in this activity is also about 1/5. So we can come into a conclusion during the process of rusting of iron powder or iron fillings in this experiment. 1/5 of some amount, 1/5 of the air has got absorbed, and we know that 1/5 of the air contains oxygen gas. So finally we can conclude from this activity, oxygen gas is getting absorbed during the process of rusting. So the component of air which is necessary for the process of rusting is oxygen gas. Right then. So we'll head on to the classroom, my dear children, and we'll write down our observations and our conclusions. Right, my dear children. Now in this activity we'll be observing some acids, some bases, and some neutral substances. As examples, we took solution A, this one, solution A, HCl solution, hydrochloric acid, HCl means, right? Hydrochloric acid solution. Second one, sodium hydroxide solution, sodium hydroxide solution, hydrochloric acid solution, sodium hydroxide solution. C, right? C, sodium chloride solution, common salt solution. Third one. Once again, A, HCl, B, sodium hydroxide, C, sodium chloride or common salt. Right. You know that HCl or hydrochloric acid, in the name itself it says acid, right? So hydrochloric acid is an acidic substance. Sodium hydroxide, hydroxides. So in the earlier grades also you have identified bases. So most of the bases ends with hydroxide part. So sodium hydroxide is also a type of a strong base that we use in our laboratory. So this is sodium hydroxide solution B. C, our common salt solution, right? So if you take common salt do not have any of acidic or basic properties. So therefore, common salt is referred as a neutral substance. It's a neutral substance. So now what I'm going to do is, I'm going to test these solutions by adding these special papers. First of all, I have piece of papers which are in blue color, right? So these pieces of papers which are in blue color are referred as blue litmus. You already know these things, blue litmus. In the materials also, I told you when I was doing the activity on the classroom, I told you that for the materials we'll be needing these litmus papers. So blue litmus, then these red color paper stripes are red litmus, Then this yellow color paper stripes, pH papers. pH papers. And to identify the pH scale and the relevant color, we have an indicator with the relevant colors. Okay. So first of all, I am going to use this A solution. So we know that A solution contains HCl, right? So we'll add some amount of A solution into this A Petri dish, right? Then I am going to add B solution to the B Petri dish and C solution to C Petri dish. Once again, A contains hydrochloric acid, sodium hydroxide solution, sodium chloride or common salt solution. Right, my dear children. So I'll remove these papers to a side and keep it in the Petri dish that I have in here. So first of all, I am going to take blue litmus. So we'll add blue litmus to each of these Petri dishes and we'll observe what will happen to the color of blue litmus paper. So we'll add a piece of blue litmus to A, piece of blue litmus to B, and finally to C. Now I am going to take each of these litmus papers. So now here, when you take these acidic solutions, it's not wise to touch these solutions from your bare hands. But in these cases, we have added water and we have diluted the solution very well. So it's not that much risky. But remember, it's not wise to touch these chemicals with your bare hands. Okay? Remember it, my dear children. So first of all, I'm going to take this one that has blue litmus. So this is the observation with the blue litmus thing. Okay. A means this acidic solution or the hydrochloric acid turned blue litmus to red color. So acids will turn blue litmus to red color. So this is a unique feature of acids. We can use blue litmus papers to identify acidic solutions. With the presence of an acid, blue litmus turns to red color. Second one, we're going to add red litmus, right? So we'll add a piece of red litmus then. Piece of red litmus, piece of red litmus, and the piece of red litmus. Right then. So here, let's see what has happened to the red litmus. With the acidic solution HCl, this is what has happened to the red litmus. Actually, there is no observation. It has the original color, right? There is no observation. It has original color, right? Red litmus. Red litmus has turned into blue color. See, red litmus has turned into blue color. Red has turned to blue color with the presence of a base. So you know that B solution contains sodium hydroxide, which is a strong base. But here up to a certain level, we have diluted it, right? But however, it contains a base. So therefore, red litmus is getting converted into blue color, right? Red litmus is getting converted into blue color with the presence of a base. That's a unique feature of base, and we can use this activity to identify bases in our day-to-day life by using these litmus papers. So when you add a red litmus to a base, red will turn to blue color, like in the case in here. Okay. Now the neutral substance, which is salt. So there is no difference with the color. The red is going to stay as the same in red color, right? Okay, now the third and the final paper, pH papers. So now I am going to add a piece of pH paper to each of these containers. So we'll add pH papers then. pH papers. Kind of a yellow color paper stripe, pH paper. So we'll add pH papers. One to the acid, one to the base, and one to the neutral substance. So we'll give it some amount of a time. So here, now let's take out these papers and we'll see our observations. To get our observations more accurately, I'll place this indicator in front of you. Right, I'll place the indicator in front of you. Right, my dear children, now let's see the color change. So I have placed the indicator here. Now I'm going to take the pH paper and place it here. Let's see a value. So it's around like between 3 and 5, right? It's between 3 and 5. Between 1 and 3, like pH value is about 2. Yes, pH value is about 2. So here, see the color? The pH value is about 2 in here. Right? pH is about 2. Right? So I'll keep the pH paper here. So in the first solution, where we use hydrochloric acid, pH value is about 2 and it is showing a red related color, like a yellow, orangish yellow kind of a color, right? So the second one, sodium hydroxide solution with pH paper. See, it is showing a good blue color. See, pH value is about 9, 10. It's about 9 or 10. See, it's showing a good blue color. So bases, if you take bases are showing blue related color. It's quite easy to remember. B, bases. B for blue color. See, blue color, blue related color, base. Then the final one, the pH paper, which is on the sodium chloride solution. So we'll compare the color. So it has like about, see here, it has a color about 5 to 6, right? 5, 6. It's greater than 5. It has some kind of a green color, some amount of a green color. So this 5 in the fifth color, you can observe the fifth color, 1, 2, 3, 4, fifth color. It has a light yellow color, but the paper which I have in my hand is having some amount of a greenish yellow color. So it's around, it's greater than 5, but less than 6, right? It's nearly about 7. We can say that it's nearly about 6 to 7, the pH value, right? So these are our observations from this experiment, right? So when you add in pH papers for acids, it's giving out a red related color. So the pH value of an acid is around 1, 2, 3 and 4. I mean, like if you take the pH value of an acid, it's less than 7 to be in exact, right? It's less than 7, right? 6 is also more related with neutral substances. But if the pH value is less than 5, then it is acidic, right? So acid is giving out a red related color, right? So blue litmus is getting converted to red color with the presence of an acid, and pH papers are also showing a red related color like orangish yellow or red color is getting we can observe like that kind of a color with the pH papers as well when you insert a pH paper into a acid solution. If you take bases, now bases have a blue related color like purple, light blue, blue color, dark green. So those kind of colors are blue related colors. So bases show these blue related colors, right? So here you can observe these things are very clear to us. All of these substances are getting, all of these papers are getting converted to a blue related color, right? So red litmus is getting converted to blue color with the presence of a base, right? And pH papers also getting converted into blue related color with the presence of a base. Now the third one, the neutral substance. There is no distinct change when you add these papers to neutral substances. There is no distinct change, right? Red litmus remains in the red color, blue litmus remains in the blue color, and also pH papers is showing some amount of a color which is related to pH value 6, 7, greater than 5, but more closer to 6 and 7, right? So these are the observations that we can take from the experiment if you add these pH papers and litmus papers for the solutions of acids, bases and neutral substances. Right, my dear children. Now I'll remove these petri dishes. I'm going to remove these. Right? Okay. I'll wipe out the surface so that you can observe these things very clearly. Now, I'm going to take each of these solutions once again. I'll be needing each of these solutions once again. Here we are going to observe the color change of these solutions with the presence of phenolphthalein. Here I have phenolphthalein solution. Phenolphthalein is a special indicator that can be used to identify bases. With the presence of a base, phenolphthalein is giving out a pink color. The normal color of phenolphthalein is actually, now I have a dropper with me. So let's get some amount of phenolphthalein to the dropper. See, the actual color of phenolphthalein is colorless. See, there is no color. There is no distinct color in phenolphthalein. So with the presence of a base, phenolphthalein is giving out a pink color. Now let's only with bases. Okay, remember the pink color can be observed only with bases. Now let's add a drop of phenolphthalein to each of these vessels and let's see whether we can get this observation. So first of all, I am going to use the leftover part of this hydrochloric solution and I am going to add a drop of phenolphthalein. Right. There is no change in the color. So I told you that we use phenolphthalein just to identify bases. So with bases, phenolphthalein is giving out a pink color. So we'll keep it in here. A solution, HCl. Now let's try phenolphthalein with B. You know that phenolphthalein is showing out or it's giving out a pink color with bases. Now B solution is sodium hydroxide. B solution is sodium hydroxide. Sodium hydroxide is a good base. So when I'm going to add phenolphthalein to this base, it should give out a pink color. We'll see. Yes. See, we can clearly observe it is giving out a good pink color. So bases can convert this phenolphthalein indicator to a pink color from colorless solution. Now the final one, the third one, sodium chloride solution. We'll add phenolphthalein to the sodium chloride as well. There is no observable change. Right? There is no observable change. It remains in the same color. So therefore, we can say that to identify bases, we can use this phenolphthalein indicator. So phenolphthalein is a substance that can turn a certain base into a pink color, right, from the colorless solution. So sodium hydroxide is a good base. Therefore, color of phenolphthalein is getting converted to pink color. Right, my dear children, then we'll head on to the classroom and we'll discuss further things related with the lesson. Right, my dear children. Now in this experiment, we'll be observing what kind of a reaction is this neutralization reaction, right? Or what kind of a change is this neutralization change. So in a neutralization change or neutralization reaction, an acid is reacted with a base or a base is reacting with an acid. So when reacting acid with a base or else a base with an acid, both the acidic and basic features disappear to form neutral substances. So I have these things with me, these materials with me. So we are going to conduct a small bit of an experiment to show that the neutralization reaction is going to occur or substances are getting neutralized when you are adding an acid with a base. Right. So first of all, I'll be needing some amount of sodium hydroxide solution. Sodium hydroxide solution. So this is sodium hydroxide solution. Some HCl solution. HCl means hydrochloric acid. So some hydrochloric acid, right? Some amount of hydrochloric acid. A vessel, right? A vessel to dissolve or to, like add these substances separately and to get a clearer observations. And I have another two separate beakers to measure these liquids separately. And finally, I have a dropper plus some amount of phenolphthalein as the indicator. So first of all, we'll measure about 30 milliliters of sodium hydroxide, right? To get more accurate observations very clearly. So we'll get about 30 milliliters of, right? We'll get about 30 milliliters of sodium hydroxide solution to this smaller beaker. So we need to keep the beaker at the eye level when you are measuring liquids. 30 milliliters to be exact. Right. So I have measured 30 milliliters of sodium hydroxide solution. Right? 30 milliliters of sodium hydroxide solution. See? I have 30 milliliters of sodium hydroxide. Then we'll take HCl and we'll measure some amount of HCl. Right? We'll add some amount of HCl. Here we don't know exactly how much of HCl is needed for this chemical reaction. So therefore I'll add like some amount of HCl to here. Right then. Now I am going to add this earlier measured sodium hydroxide solution to our vessel. Sodium hydroxide solution. Now, gradually, before that, to get an observation, we need to add our phenolphthalein solution. So you know that phenolphthalein is giving out a pink color with the presence of a base. So we'll add phenolphthalein into this. Right? Have to mix it very well. Right? To get more clearer color. So we'll mix it. So I'll add another drop. Right. See, phenolphthalein is giving a good pink color with the presence of a base. So I took sodium hydroxide. So it's giving a good pink color with sodium hydroxide. Right. Now I am about to add previously measured hydrochloric acid to this solution of sodium hydroxide. Observe what happens when I am going to pour this liquid into the vessel. Okay, this liquid is hydrochloric acid, HCl. So we'll add very gently. Right? Right. So we'll mix it. Now, when I am adding this hydrochloric acid, at a certain point, if the solution is getting neutralized, if the basic features are getting disappeared, then this solution should become colorless, because phenolphthalein is originally in colorless situation, right? So when adding acid, it should be turned into a colorless solution. So we'll see whether it is getting colorless, whether it is getting into a colorless solution or not. We'll add more. Remember to add it slowly, my dear children. Okay. Right. So we'll mix it. Let's add once again another like 2 or 3 drops. Right, you can see the color is getting changed somewhat. Right, just 1 drop once again. Right, now it's difficult to put by using this container or this smaller beaker, so therefore I'll use the dropper. So say let's take some amount of HCl, right. You can see the color is getting disappeared gradually. In the earlier it was like dark pink color, but now gradually the color is getting decreased. So we'll add drop by drop. See, the color is gradually decreasing. We'll add another drop. See, the earlier it had a good pink color, but now the color has reduced somewhat. See, you can observe now the color has decreased dramatically. Now in the earlier situation it had a good pink color, but now it has a very less pink color. We'll add another drop and we'll mix it. See, now the color even drops down. So here now you can see in this solution the pink color is very less, means now it is about to get neutralized. It has some amount of a basic nature as it is in some amount of a pinkish color. See, it has some amount of a pinkish color, so it has some amount of a basic nature, right? So when adding acid to this sodium hydroxide solution, you can observe the colorless or color is getting dramatically changed into the initial color of the sodium hydroxide solution, which was colorless, right? So it doesn't have any basic or acidic features when I'm going to add, when I'm going to add these HCl or else acidic substances to sodium hydroxide solution. The basic nature of the sodium hydroxide solution gradually reduces. That's why the pink color is also getting reduced gradually, right? So we'll mix it once again and we'll add another drop to see what will happen to our solution. Right, my dear children, now you can observe the color has got disappeared totally, right? Means that now if you check this solution, there is no pink color in it, means that this solution has become now a neutralized substance. That's why there is no pink color. Initially it had pink color because it contains sodium hydroxide solution. So when I'm adding hydrochloric acid into the sodium hydroxide solution, gradually the pink color decreased and it took a colorless solution, right? Now it converted into a colorless solution. It's because that there is no acidic or basic features within this solution that I have in my hand right now. So we can finally conclude that from this experiment, by adding acids with bases, we can neutralize or we can cancel off both acidic and basic features. Right, my dear children, now see, you can observe the colorless solution. Now I am going to show that when I am going to add some amount of sodium hydroxide back to this solution, I'm going to add some amount of sodium hydroxide back to this solution once again. Now this is the solution that we had, right? This is a solution that we have right now. This, I told you that this solution is now a colorless solution. Earlier it had a pink color. Now it is colorless. It's because that this is a neutral substance right now. That's why phenolphthalein can't give any color change, because with neutral substances, phenolphthalein can't give any color change. So I'll add just 1 of 2 drops of sodium hydroxide solution back to this solution once again. See, as soon as I'm going to add sodium hydroxide solution once again, the color is going to reappear. See, once again color is going to reappear. Means that once again the basic nature of the solution is going to turn back on. If I'm going to add more, see, if I'm going to add more, then once again it will take the initial dark pink color. See, so when I am inserting this hydrochloric acid once again, it will turn into like a colorless solution. See, right. So we can say that when you are reacting or when you are mixing an acid with a base, both the acidic and basic features disappear to make neutral substances. So children, will head on to the classroom and will write down our observations and our conclusions from this experiment.